There is grandeur in this view of life.
Welcome to Evolution Talk with Rick Coast, an introduction to the oldest story ever told.
The problem is couched in terms of gene exchange. The way it's defined classically in the speciation literature is biogeographically, that is, in terms of geographic relationships. So we have this tension between geography on the one hand and gene flow on the other. Everybody thinks they're the same thing, but they're really not.
That was biologist Jerry Coyne. For today's episode, I thought we'd revisit a topic that we've looked at a number of times on this show. But it's actually been a while. So if you're new to the show and haven't gone back to listen from the beginning, which is a lot of episodes, so I get it, then this show is for you, especially if you've ever wondered how new species evolve. Now, there are some folks who are of the mind that it can't happen. They get that a particular animal can change over time or evolve over time, but not into a completely new species. It's hard to fathom how an elephant can possibly have a common ancestor with, say, a mouse. But they do share one, but that was millions of years ago. It takes time. Unless you're an evil genius, you can't take a mouse and suddenly transform it into an elephant, even if you set aside a few decades of your life to achieving this goal. And I'm sorry to say, at the end, you'd still have a very frustrated family of mice. And that's why some folks have a hard time grasping the concept of speciation in nature. You can't see it happening. It's slow, extremely slow. Millions, if not billions of years slow. Who has time for that?
Ain't nobody got time for that.
So how does it happen? Let's say we do have 1,000,000 years to sit back and watch a species evolve. Let's say you're at a dinner party and bump into the Count of Saint Germain, and he offers you the elixir of life. You now have the time you need, so you put out some cheese, strategically placed with some traps, and wait for some mice to show up to take the bait. Now that you have your mice, you sit back and wait. But nothing happens. You wait and watch for 10 years. You even let them run around in a large enclosed yard. Generations come and go, but they all look just like the mice you caught all those years ago. You wait another 10 years, and then 20, and then you declare your experiment a failure. And then someone comes along and tells you that you've done it all wrong. You haven't given evolution a chance to do its thing. Your population of mice running around in the same yard for generation after generation, well, they've been safe and sound. With no environmental changes to contend with, and no strain on resources or competition for those resources, that mouse population has found its ecological niche. Genetic mutations may occur now and then, but they quickly fade away, having offered little benefit in the grand scheme of things, at least in the grand scheme of the yard you placed them in. So what gives? What does it take to create a new species? Let's ask noted biologist Ernst Mayr what he thinks.
New species originate when two populations get geographically isolated, and in this isolation, either by a branch of the ocean or by a vegetational barrier, let's say a desert or a savanna, in the case of forest birds. During this period of isolation, there is enough genetic turnover in these populations so that eventually these two populations are so different that they react to each other as if they were two different species.
Imagine you've been given an evolution kit as a gift. You open the box, eager to get started, and you find a piece of paper. That's the instruction manual. You unfold it, expecting a complicated set of rules to follow. Nope, nothing complicated here. You flip the paper over, expecting to see maybe a bit more. But no, there are only 3 steps given, and time, much like a recipe. Add this, add that, mix it up, stick it in the oven, and wait for 20 minutes. Let's look at the instructions in your evolution kit. The first step in the process is isolation. I don't mean like the mouse population you started with. Sure, they've been isolated, but all in the same place for a few decades. You need to split them up. You could place them in another yard that's exactly the same. Speciation may occur, but chances are it will take a lot longer than what you'd hoped for. You may see some differences after a million years, but it's unlikely you'll see anything to write home about. You'll still be of the mind that evolution can't create an entirely new species. So let's try again. How does nature do this? Well, it follows the same set of instructions as the ones in your evolution kit, but on a much grander scale. But don't throw them away yet. We still need them. So for natural selection to have something to work with, an animal population has to first become split apart and separated from one another. Now, this could happen in a number of ways. A group could wander over a land bridge between islands and that bridge could sink after a storm. Or maybe a school of fish might swim down a tributary to another lake and that tributary dries up. Whatever the geographical barrier is, somehow one group is physically separated from the other group. That's the first step in the process. You can check that one off. Now natural selection can get to work. With the populations separated, there are different pressures for each population to deal with. The first group might have an abundance of food and nothing ever changes. Again, mutations might occur or do occur, but without providing any sort of advantage, those mutations might disappear. Or stay. There really are no rules. Mutations happen. They may persist or they may not. It all depends on if that mutation gives the organism an advantage over one without the mutation, like with this second group. Maybe the environment the second group found itself in is different in some ways. Maybe the food's scarcer. Or maybe they prey upon small insects, but these insects that they find here are faster than they are used to and harder to find. Perhaps the insect nests are situated in trees, whereas before, where the group came from, they were closer to the ground or even underground. In some cases, the group might gradually perish. Or a mutation occurs that provides a benefit. It doesn't really have to be a big change. Small ones will do, as long as they provide even a small benefit. Stronger legs, keener eyesight, slightly sharper claws to cling to the bark of a tree so they can reach higher. Well, some changes do nothing and they disappear, as I mentioned. But if a mutation adds to the organism's ability to get to a food source and survive a little longer, long enough to produce offspring, then that change sticks around in the population. Maybe it's colder in this new environment, and a mutation that allows for longer, more dense hair occurs. Let's look again at your steps. The first step was isolation. Well, we're all set there. The second step is for beneficial genetic mutations to accumulate. We see that happening here with one group. Sharper claws, stronger leg muscles, thicker hair, a population which can climb the bark of trees to get to its food source. That other group, the original one, has slightly longer facial whiskers than it used to, and there's variations in hair color that weren't there before, but nothing earth-shattering has happened. They still look relatively the same and have accumulated some mutations which persisted only because they didn't affect the organism in a negative way. Well, let's take an example. Say a predator entered the scene which could easily spot organisms which stood out on the forest floor, like white fur. What happens if a mutation allows for brown fur that blends in? Well, those organisms will have an advantage over the ones with the white fur. As a result, over time, all that will be left are those with brown fur. If the predator disappears and a white fur mutation pops up again along the way, you may see that one gradually come back. Not so different from, say, leg warmers, denim jackets, and bell-bottoms. Fashion trends do tend to come and go. So, what's our third step of the process to create a new species? The inability to exchange genes. So what does that mean? Well, that means the two populations, were they to be reintroduced to one another somehow, someday, they can no longer reproduce. When two populations evolve separately under different selective pressures and can no longer reproduce and exchange genes, what do you have? You now have two separate species. I also mentioned something else, didn't I? Time. You also have to give it time, a lot of time. Imagine all these changes and genetic differences accumulating over millions of years. Genetic changes that allow for body size, hair color, brain size, sight, arm length, all selected for because it allows the organism to survive long enough to pass those genes on. Mutations which accumulate over time. Simple, right? Isolation, genetic divergence, a reproductive separation. Give it a few million years to bake, and you have a different group of species running around. And it happens over and over and over and over and over. Now, everything that I've just described to you is a process called allopatric speciation. Of all the ways speciation has been theorized to occur, allopatric is the most common and widely accepted. It's also the easiest one to comprehend. Separate a species into two groups, provide a barrier that neither group can overcome, and let nature do the rest. If one of those groups, or even say both of the groups, face extreme obstacles that make survival difficult, well, variations will spread fast, providing those variations are favorable, of course. In an absence of extreme selective pressures, variations will spread slowly. Charles Darwin saw this with the finches on the Galapagos Islands. Each island's species of finch is evidence of allopatric speciation. Different beak sizes are a testament to this. Each species' beak serves its purpose when it comes to feeding on the various types of insects and the seeds that the finches encounter on their respective islands. If we want to make things a little more complex, and why not, right? There are two varieties of allopatric speciation. There's vicariance and peripatric. Vicariance is what we've been focusing on already. Geographic barriers between two groups that makes gene sharing between the two pretty much impossible. Peripatric speciation is, well, I'll let the master Ernst Mayr jump in again.
Species develops a new colony, a founder colony, beyond the species range by some individual crossing over unsuitable terrain beyond the species range and establishing this new colony, which eventually expands into a large population and owing to this barrier between it and the mother country and the mother species eventually develop into a new species. And I call this peripatric speciation.
For all intents and purposes, the differentiating factor between vicariance and peripatric is the size of the separated population when compared to the original population. If the isolated population is small, well, so will be the evidence of genetic variation. But sometimes it's obvious. A good example of this, actually, is the polar bear. The polar bear evolved from the brown bear, not because of a strict geographical barrier, but because a small group separated and lived on the fringes of the first group. This smaller group is often referred to as the founder population. It's a very difficult distinction to prove, however, given that both types require a barrier to prevent gene flow. But it's all about slow, incremental changes. If a group can interbreed and share changes in the gene pool, well, then the members of that group are the same species. Disrupt the gene flow, and speciation can occur. Does it always require, say, a dramatic and insurmountable geographical barrier between the two? Well, no, it doesn't. This is where we get into two other types of speciation: sympatric and parapatric, not to be confused with peripatric. But those we'll save for the next episode. See you then. I hope you enjoyed today's episode of Evolution Talk. I'm Rick Coast, and you can find show notes and source material and also ways to support the show at evolutiontalk.com. I'd love to hear from you. I hope your week is going well, and until next time, please take care of yourself.
Evolution Talk is a Rick Coast production.